Sorry, I'm not a doctor. That doesn't mean that all of this is false. Okay, let's see if this works. So quantum spring theory is a rather elaborate title for a series of models that I'll give you some idea of where all this comes from if I have time. Putting the fizz back into physics. Not just the bounce and the bubbles, but also the physical. So I've heard calls in this conference for a paradigm shift and also calls for models of the nucleus. And in this little talk, I'll present the paradigm shift and models of the nucleus. How convincing this is remains to be seen. What is the common thread to all successful LENR trials? Fusion, right? And what's common to all fusion events? The binding energy, or mass defect, right? Okay, so what do we know about binding energy? This is old data. The binding energy per nucleon. So you start over here. I don't know if we have the pointer, I guess not. But you start over on the left hand, your left hand side with deuterium and go up to tritium, and then the peak there is helium-4. And what you're measuring here is how much binding energy there is per nucleon as you add the additional nucleons to the nucleus. And this has been a very mysterious curve. It's the best data we've got on the nucleus. It's well measured, and there are databases on this stuff. It's non-monotonic, as you see. You might have expected this to just keep rising. Those guys, you're all in the field. You know how this works, right? But there hasn't been a good model for this yet. But this is at the absolute heart of LENR. If we don't understand how fusion works, how are we going to, have a model, a theory of fusion that's going to guide our experiments? Well, let's take a look at some of the models that have been proposed. Most of you will be familiar with this, so bear with me. The liquid drop model was the first one that came along. The nucleus is a drop of liquid. You're adding, each time you add a nucleon, you add another drop. And you get this circle curve that matches the shape very, very well. I think Gamma did this originally quite some time ago. It's been refined over the years. The absolute error isn't very good in here. The correlation's terrific because it matches the curve well. It's not clear that any of us believe that the nucleus is a drop of liquid. Norman Cook gave a great talk. He's very familiar with this work, very much a pioneer of it. It came along about 1985, and it's well covered in his book, which I will sell my copy. I've decided it will be more than $700. I love the book. The absolute error here is terrific, 5 times almost improvement on the previous, but the correlation kind of drops off because, as you can see, the experimental data deviates from the actual shape of the curve, right? So this was the next best that we got. Now I have to talk a little bit about the independent particle model because this is the model that everybody believes actually is the model of the nucleus. It's based on the idea that the nucleus has quanta like the electrons have quanta, and therefore these peaks that you saw in the binding energy curve are when the quanta get filled. And that's kind of the model. But as we say, where I come from, that dog don't hunt, because there's no room in the nucleons for things to orbit around. Not as we understand the size of nucleons and the nucleus. There's no room in the nucleus for things to orbit. But the main problem with this is it just can't say anything quantitative about the binding energy. And so it's hard for this model to guide us as practical experimental physicists because it can't tell us anything about that binding energy curve, except that qualitatively it has peaks. This is our data. Now, when I first came up with this, I thought, well, that's nice. The absolute error is pretty good. The correlation's pretty darn good. How did we arrive at this? Well, this came from somewhere completely out of left field. I started working on a problem. I've got a little bit of extra time, maybe. Do I really have the 20 minutes, or do I only have the 15 minutes? It doesn't matter. I'll tell you very briefly how this all started. Back in the 70s, my daughter was 5 years old. We were having this conversation about all this pavement that are the roads, right? And she said, well, this is stupid. They should be parks. We should be able to walk along the roads. Instead, we have all these cars. And she said, we should float around in the sky in air chairs. And I said, well, we don't understand what causes gravity. So we can't do that yet. And she said, well, you work on that. And I said, you indulge your 5-year-old daughter, right? Sure. So I started to think about it. And I thought about it in my spare time for about 20 years. And I had an idea. And the idea goes, well, first let's talk about what is the result of what I found. What I claim is that if we went back 100 years to when quantum mechanics was first thrown out, and by the way, there was a lot of debate about quantum mechanics in the early years about how to interpret it, right? And what it really means. We've forgotten a lot about those debates, I think. But if we knew what we know now about particles, about all that we've learned about particle physics in the accelerators and so on, I think we would draw different conclusions about what's going on in the subatomic world. And I actually think, and I've heard this mentioned at this conference already, that the classical laws of physics do apply subatomically. But space has unique characteristics. So let me tell you where this all comes from. And I know that this is going to all seem very odd, but bear with me because we get great results. Suppose you have a box of space, okay? V of SB, volume of space in the box. I'm a physicist, right? And we put a particle in the box. And the question I want to ask you is, how much space is still in the box? Is it the original amount of space less the volume of the particle? Or is it the original amount of space still in the box? And quantum spring theory says it's the bottom one. So what we think is matter does not replace empty space when a particle is created. It displaces the space. Space is compressed like a spherical quantized spring, and it takes force to set a spring, which is all the energy you put in to create the particle or the photon. So it runs right down through the energy spectrum, and the spring pushes back. And we've heard about the stiffness of space being mentioned, and space is kind of stiff, but it's not stiff enough for a proton to stay, to keep the bubble open without help from the quarks. So protons have content, photons don't. I can't talk about all of this stuff. Is there any evidence for this mad idea? I think there's a lot of evidence. The hydrogen nucleus is larger than the proton. But there's only one thing inside the 1H nucleus, and that's the proton. So this is measured with electron scattering, right? You throw electrons at the nucleus, and you find out by how they bounce off how big it is. And you get a picture like this. This comes from hyperphysics. And you can go to nuclear size and hyperphysics, and you get this picture. And notice how the actual measurement, there's two things about it I want you to notice. One, it's well larger than the proton, okay? And two, it's kind of a soft edge. It's not a sharp edge, okay? So here's our picture. This is going to be a bit of a leap for us, I think. So we've got our proton. It creates a bubble in space when it's formed. It pushes space out. Space is compressed into this sphere around it. So the proton force on space that's created by the energy that you put in to create the proton. We get the nuclear skin on the outside. By the way, the nuclear skin is mentioned a lot in Norman Cook's book, and it's present on all nuclei. There isn't a great explanation for this, by the way. It's always there, and it's always about this size. And then we've got the strong force pushing back. So It's the energy you put into create the particle that pushes space out, and you get the spring effect of space coming back down on the particle, and you get this quark structure, which I've happened to arrived at a buckyball for this structure, but it could be some other structure, or no structure at all, just quarks in there running around, keeping things at bay. I have no idea because I've never seen the inside. I just made a hypothesis. I tried some other shapes, by the way, cubes and tetrahedrons. They didn't work too good. But this works pretty good because as you see up here in the corner here, the little red bit where it says binding energy, when that spherical cap is cut off because this particle comes up and nests against another particle, that's the mass defect. That's mass is lost. That's your binding energy. And this is how we get that curve. And the thing to notice about this is in the buckyball, as it turns out, there are two different spherical caps, hexagonal caps and pentagonal caps. The hexagonal caps are a little bit bigger. So we get two quanta, two different sizes of binding energy that we can work with, which gives us three different combinations when we put particles together. Two pentagonal caps, a pentagonal cap and a hexagonal cap, or two hexagonal caps, right? Wonderful. Just a little bit more on this. The space around the particle is compressed, and that causes the electrons to scatter like we saw in the previous diagram. And by the way, it just happens to be the radius of that space just happens, as measured, just happens to be the wavelength of the proton. And the wavelength of the proton is, as you can see, speed of light times Planck's constant divided by the energy it took to create the proton. Which means that the particle and the wave are always there all the time. It's not one or the other depending on how you observe. So I've heard at this conference, maybe there are parts of quantum mechanics that aren't applicable as much because we've got more experimental evidence now than we used to have. And this is part of that story. So, mass defect. Proton comes together with a neutron. We've got up quarks in blue on the proton, and the down quark in the middle. Pretty fanciful. Actually, the number of segments do relate to the actual masses of these particles as measured, as best as they are. They're not well measured. Neutron has two down quarks and an up quark in the middle. By the way, it's pinned to the side so it doesn't rattle apart and decompose in 15 minutes, or apparently the new measurement, 10 minutes. And there's our lost spherical caps. And that's the binding energy of deuterium. So what's important? Classical mechanics applies at subatomic scale, and LENR is a problem in materials and mechanics, which really puts it on a completely different footing. Now, it doesn't mean that there's any contradiction between this model and other ideas we've heard here today and yesterday. It just means that there are multiple models looking at this problem from different angles, and they all have something to tell us about what's going on here. So what are the physical conditions we need? A stable target nucleus, an impact nucleus. That's it. So this whole talk came from David Nagel's paper, which is about to be published, where he challenges us with theories about LENR to answer, 24 different observations that he's made across a large number of LENR experiments and 10 different questions that have been asked. So nuclear reactions can be initiated. So I'll just talk quickly about the observations, just a few of them. Nuclear reactions can be initiated with low energy. Some LENR occur in small and distinct regions near the surface. For electrochemical experiments, high ratios of deuterons to PD atoms favor LENR. These are just observations that I think we all know from the experiments that have been done. And a few measurements show that LENR has a very rapid onset, which I think is actually quite important. What can we conclude? What does quantum string theory say about these questions? It says these are the conditions that are likely to attain the Fermi velocity, which is the velocity you need to overcome the Coulomb force. So there's one idea. There are at least two other ideas, or three other ideas in this conference. The two we just heard in the two previous talks, and the one from yesterday from Zapiro that is yet another idea. It It's important for us to understand which one of these is the correct model, or which set of them. I don't know, but that's what that. I didn't know about those talks when I did the slides, so you get what I knew at the time. Connection to LENR from our theory. Well, we've got the architecture of fusion nailed. Mechanics work at subatomic scale. I think that puts us on a different footing. The foundations of the concept are that the mass defect is in the spherical cap. It doesn't matter what the hell's on the inside, really. It does matter that there are two different kinds of caps, or losses of energy, mass defects. How many steps does it take to do LENR? Well, load the target, shoot deuterons at it, or hydrogen. Equations written, yes, well, at least for our understanding of how fusion works, that's been published rather a while ago. It took a while for me to understand that was relevant to our topic today. Pretty good accuracy, as I've mentioned. We do explain the 24 observations, but I didn't go over all of them now because there isn't time in the talk. I can't predict how long it takes to load the target or how long fusion will last once the target's loaded, because it just depends on too many variables. If you're doing it electrochemically or with gas or some other way, what the material's like, I couldn't answer this one. Do we explain all of LENR? Well, everything except maybe why we don't get gamma out when we get our helium formed. But I actually have a hypothesis around that now, and I think there were other good explanations in this conference that are probably much better than my conjecture anyway. So maybe we'll team up and form a meta theory that will explain everything. Is the theory testable? We think so. So I formed a little company. I've filed a patent. I'd like to build a prototype. If anybody has any spare change, come talk to me. Yes, I think we can test it. I can't say a whole lot about that unless you sign the NDA, because my potential investors would get unhappy with me. But I do think there's a potential to test all this. So, yeah, that's about it. So, any questions? Do we have time for questions?
Yes, we have 3 minutes, maybe. First question, please.
I could ask a number of questions, but a couple that come to mind. Is your buckyball an emergent property? Do you view that as something that emerges? And can you account for spin, dipole, and gravity?
Okay. The buckyball is formed, if there is such a thing, when the particles form. So I'm not sure if that counts as emergent or not. I don't understand the time scale. I have no concept. Can I talk about spin? No idea at all yet. You guys are going to help me with that. Gravity, absolutely. There is a paper before this paper where I talk about what causes gravity. It kind of needs to be revised based on what I've learned in the last 9 years. So there's definitely stuff on it. Some of that is covered in the poster session to some extent. But it's basically those nuclear quanta, when they come together between two particles, they want to go back to that home position, where it's the radius, the natural home position of the radius, and that's what causes gravitation between all the particles.
And one other thing, obviously you're thinking that space has inertial qualities of its own without any.
That's kind of right.
So you didn't like the liquid drop model, I see.
Well, I didn't think it matched the data very well. That's all I'll say about it.
Okay, so people have been interested in that in recent times. So people started working with Thomas Fermi model, which is closely related to liquid drop, or the liquid drop can be derived from it. And then people work with kind of density functional, closely related to Thomas Fermi, and they corrected it and they generalized it. And they've been fitting it to, getting versions of it that are fit to the known masses. And the general agreement these days is awfully darn good. So there's probably 30 or 40 papers out there with models that compare against the modern masses. I can send some of them to you. You might get
That
a
would be
kick out of it.
wonderful. I'm out of date there, and I apologize. That's very interesting.
Last question.
My name is Bokar. I'm electrical engineer, new to this cold fusion, and I have a crazy question, crazy questions, and many people call me crazy. And I expect when you mentioned one of the slides, you said layers, first layer. How many layers are there in hydrogen atoms?
Oh, I think those layers, those nuclear quantum layers go right out, just like the electron quantum layers do, right? They start when the particles formed, and I think, conjecture, they go out at the speed of light to, to
Unlimited? Unlimited layers?
unlimited.
Because I expect some definite number of layers.
Well,
It cannot be like open.
my understanding, now I don't know everything by a long shot, but my understanding of electron layers is they're also thought to continue to go out past the last one that's usually occupied. I think that's the general consensus.
Do you advise me any reference thing to just reading more and understanding about
Unfortunately,
them?
this whole idea of having nuclear quantum layers is kind of new. So you'll have to look at my papers, and then the rest of you guys will have to help me make this theory make sense.
Thank you.
Okay.
Thank you, Dr. Blake. This section is closed, so see you tomorrow morning, please. Okay.
Thank you very much. Sorry to hold you up another couple minutes. First of all, let me emphatically thank all the speakers and the embattled session chairman. They had a good day again. Thank you very much. 15 years ago, roughly, Bill Collis did a tremendous service to our community by founding the International Society for Condensed Matter Nuclear Science. So he's having his annual general meeting now in this room. The society, as you know, does very important things. It has the Journal for Condensed Matter Nuclear Science. It organizes conferences in Europe, another one coming up this fall. So I hope you can stay and listen to what Bill has to say during the general meeting. And I remind you of Norman Cook's meeting at 7:30 tonight in what, room 322, is it? Yeah, so that should be a good show with computational treatment of his lattice theory. Thank you very much.